In section 7.3, we're going to leave behind the ideas of parametric equations and begin to start looking at polar coordinates. And in 7.4, we'll start talking about how we do calculus with polar coordinate systems and functions. So if we take a look here at the start, we'll see is that I'm going to first draw a comparison, or at least a compare and contrast, between our regular old Cartesian coordinates, or rectangular coordinates, and polar coordinates. Now some of you may have seen things like this before, possibly in classes you've taken a long time ago, but it's always worth it to review, and of course if you haven't seen it, this is a first introduction. Remember that when we're working with rectangular coordinates, our classic x and y axes, we thought about navigating around the plane by giving directions about moving in a horizontal and then a vertical direction. So to arrive at any point out in space, right, there was always some sort of set of coordinates, like move 2 units over, and in this case you move 3 units up. And so we had coordinates that were representing x and y movement. Now while that's one way to actually navigate around the plane, it's not necessarily the only way. And in fact, we very rarely ever actually move around the real world in this sort of a structure. I mean, maybe if you were like walking city blocks, you would imagine that you have to move in this kind of grid, square-like pattern. But more often than not, we're really going to be working with something close to polar coordinates. Now, polar coordinates is, again, the same idea. We want to just navigate to a point in space, but I'm going to give directions for how to navigate to that point a bit differently. I plot points by ultimately rotating by a given angle and then moving a specified length. So if I wanted to move to a point like over here in space, and I imagine that I start at something similar to what we would call the origin. In this case, we refer to it as the pole. We would say, well, first what I'd have to do is if I was originally staring out in this direction, down what we call the polar axis, I would have to kind of rotate upward. At least in terms of where I was looking, I'd have to kind of look down this 45-degree angle line. So I'd imagine standing here, I would have to spin until I'm facing the right direction. And then, if someone just told me how many steps to take or how far to walk in that direction, I could eventually land at a given point. So what we'll see here is that our coordinates are going to be modeled or given by a theta value, an angle that we have to rotate, and an r value, which is standing for a radius, or how far we're going to walk. So we ultimately have our coordinates here as r comma theta. Now the only thing that tends to be strange about this set of coordinates as it's given is that oftentimes we'll think about plotting or graphing out this theta angle first and then going with r, which is kind of the reverse direction of how we often thought about working with x comma y points. Well, let's take a look below at example number 1. You'll see here I've kind of put down one of these polar pieces of graph paper. And I'm going to imagine again that I'm standing right there at the middle. And I'm going to try to figure out where each one of these different points are. Points A, B, C, and D. So let's take a look here at point A. Again, it's important to keep in mind that my second value here is my theta, and my first value is an r. So I'm going to go ahead and say first I want to face the angle of 5 pi over 6. Don't forget that pi is exactly the same as 180 degrees. So of course if I divide that by 6, that's the same thing as saying 30 degrees. If I just multiply that by 5, that should be 150 degrees. So I'm going to kind of start by staring out in the direction of 150 degrees. I haven't moved anywhere yet, but we've just kind of rotated. Remember, we're always going to start by imagining that we're staring in this direction out towards 0 and then rotate a specific amount. So now that I'm facing this direction, I have to be told how many steps to take. And if I'm told to take 2 steps, notice that's the purpose of these kind of concentric circles that I have here. This inner circle is a circle with radius 1, outer circle or middle circle here is radius 2, and my outermost circle right now is radius 3. If I wanted to have graph paper in polar coordinates that was able to graph more points, I'd have to kind of continue to draw more and more circles around this central point. So in this case, since I only want to take 2 steps, it seems like I'm going to go out to here for step 1, and then finally over to here, that's step 2. And so there's my point of A. Now notice I can do the exact same thing if I worked with point B. This first says rotate pi. So I say, okay, so I'm going to imagine I'm staring out towards 0. If I rotate pi or 180 degrees, I'm going to be staring out in this direction towards 180. And now, as I'm staring, excuse me, if I'm staring in this direction, and then I'm asked to go ahead and take -3 steps, that would indicate that although I'm looking towards 180, I need to take 3 steps backwards. And so I would go back to 1, back to 2, and then over here is where I would land for my point B. I was staring towards 180 and took 3 steps backwards. So that's the significance of the R value being negative. Let's take a look here at one more. I want to go ahead and rotate -pi/2 radians and then take a single step. So that, of course, being a -pi/2 radians would mean that I have to rotate downward this way in terms of where I'm looking. And that would mean that I am going to be staring straight down towards this 270. If I take a step, I'm going to land right here at point C. Now I'm going to ask you to go ahead and see if you can figure out where point D is going to land. I'd ask you to pause the video, give it a shot yourself, and then of course unpause to see me go through the solution. Okay, so if you actually did work through that, you probably saw something kind of strange. Maybe you had a second guess yourself. If I had to spin 450 degrees, I'd have to spin one time all the way around. That's 360. I'd have to spin an extra 90 to get up to 450. And if I'm staring up towards 90 and I have to take a step backwards, I'm going to land right on point C again. This is very, very strange. What we'll notice is that there were 2 different sets of directions that led me to the exact same point. Notice that's actually not even possible to happen in our regular Cartesian or rectangular coordinate system. There's no way that anyone could give me a different set of directions and have me arrive at the same point. But in polar coordinates, that is possible. If you take a look at the next page, you'll see how I've kind of summarized this in the note in the box below. There are actually infinitely many ways to write coordinates of a point in polar form. So, to form the same point with different coordinates, we'll simply use an angle that is coterminal, or that is points us into the same direction as our original value of theta. So notice what we're saying is that I could actually come up with infinitely many more points that land me at this C, D hybrid point. You could imagine saying, spin in a circle 50,000 times, whatever angle that would be, and then rotate 270 extra degrees. Then you're facing downward, and take 1 step. You can do the same thing by rotating backwards, or ending with any angle that leaves you facing straight up towards the 90 and take a single step back. And so there are infinitely many ways to do this, and a lot of times it's just by going ahead and manipulating the angle that we're working with.